Okay, so it's my pleasure to introduce the next speaker, Larry Gibbs, who's Associate Vice Provost for Environmental Health and Safety at Stanford University. Stanford, in my mind, and I admit to being somewhat biased, has been a leader in the area of academic environmental health and safety for a long time. And so some of the really important contributions that they have made have included, for instance, the development of a really wonderful chemical inventory system that's now used broadly across a lot of different academic institutions. And so no surprise that Larry would be a leader in this initiative as well. We're delighted to have you here today, Larry.
Thank you, Hillary, and thank you. And I want to welcome CIN, DTSC, and everyone else, and thank you very much to all of you for allowing me to be here today. What you see up here on the screen in the lower left is an example of buckyball, a C60 buckyball. I had the opportunity yesterday to join a panel at Rice, which is celebrating the 25th year since the discovery of the buckyball. And I'll talk a little more about that because I think it has a relevance to what goes on in academic research, and we're going to see some of that occurring. What I want to cover today is just a little bit of an overview in ENMs, or Engineered Nanomaterials used in academic research, and what that really means. Talk somewhat about risk assessment, risk management, expand a little bit on some of the things that Paul looked at, and applying some of those approaches in the research laboratories. I have a question. Is there a need for a unique engineered nanomaterials protocol in the research environment? We can talk about that. When we talk about the uniqueness of the laboratory, the academic research environment itself, and what they're engaged with already, and then talk about a project that's going on developing practical safety practices and procedures for health, safety, and environmental management for engineered nanomaterials in laboratories. And this is a collaborative going on between DTSC, universities and colleges in California, representatives of university and colleges in California, and NIOSH. I think it's one that is going to be very beneficial to higher education and academic research everywhere. The reason I mentioned the Buckyball Conference, this is just an indication of the amount of research activity going on in higher education, which is the primary promoter of publications related to nanotechnology. And this is just a distribution by country or country block through many years, the total number of nanotechnology related publications. And this becomes important because much of this derives out of university research settings. The interesting thing, as I was relating to yesterday, being at Rice and their celebration of the 25th anniversary of the discovery of the buckyball, we got a chance to listen to two current Nobel Prize winners. One was Robert Curl, who was one of the co-discoverers, and also the most recent, which is Andre Geim, who just this year won for his work, along with others, on graphene, which is the most recent Nobel Prize delivered in the area of nanotechnology. So you can see the relative importance that this is taking in the overall scientific community as well as potential applications. This slide just shows that a relative spread of where nanotechnology work is going on. This is a slide on the Woodrow Wilson site that you can always look at to see where is the concentrated effort going on in the nanotechnology field. And the bottom slide is what I wanted to emphasize. Much of this effort right now, in discovery at least, is going on in universities and colleges and government laboratories that are working with nanotechnology of some form. These are just the two surveys. I couldn't find much specifically on surveys that worked on specifically academic research. This is a 2006 survey by ICON, where they did a survey of all types of workplaces, and they only had 6 respondents from university representative laboratories. And in that, they found that 50% of those entities had a nano-specific environmental health and safety program. More recent publication, 2010, very recently published, but out of Spain, did a number of survey questionnaires that went out. Did not have a very high response from the United States, so this represents pretty much people working in academic research around the world, looking at how many use different aspects to control the airborne aspects of what they were working with and put controls in place. So they're really focusing on controls. You can see that there is less than 100% that are using different types of controls by any means. And I just want to emphasize that's primarily outside of the United States. Well, I want to give a little history now of what takes place and what have we done at Stanford, and then at the end of that we'll talk about the California initiative. But a lot of this activity has been derived from the 2009 letter from the Department of Toxic Substances Control on the initial carbon nanotube call-in for information. And in that, one of the things that it was a call-in for anyone who manufactures or uses carbon nanotubes in California. Much to the surprise of many of us in the academic realm, it included all of the researchers in academic research as well, based on the definition that was applied, and that was fine. So what DTSC was asking for was a response to these specific questions, and it took us a lot of debate internally and deliberation to try to figure this all out, but it also led us to really refocus our efforts on trying to identify what we have where, who's using what, and when. And so that was a very good benefit from all of this. So how we went about that was in 2009 created a survey, and initially we went, one of the things in higher education, you have the academic community has its own blogs or listservs going on oftentimes, and we found there was a listserv of people who had an interest, an academic interest in nanotechnology, and that had 130 subscribers of faculty across 18 departments. I was able to find that out by working with some of the leaders on the nano development areas on campus. After we did an initial screening with those 130 faculty, we actually identified there were only 33. There were 33 faculty specifically that had active research going on with involving nanomaterials. Now subsequently we did a detailed survey with those 33 and we got 100% response to our survey, and we can talk about that later why, but that was a very good response. And we queried the academic community, the principal investigators, the faculty, on what they were doing with the nanomaterials, what they were, and how they were being used. And in anticipation, as many of you may recall, the Department of Toxic Substances Control said their initial call was going to be for carbon nanotubes, but they were probably may have a later call in for other types of nanomaterials. So one of the things we wanted to do is not continually have to do survey after survey to reach out to see what people are doing. So we did a pretty comprehensive survey of identifying who is using what through these different types of nanomaterials and anything else that they might be using, and got a very good response. So we got 100% response. The result of that survey indicated that we have many, many departments that are working in actively using nanomaterials of one sort or another. It doesn't mean they're producing them, but they are using them in their research. And the spread of departments runs from the medical school to engineering to basic sciences, etc. The typical thing that you would see now in most academic research going on at many larger research universities. And the materials are spread as well. There are materials, all kinds of different nanomaterials are being used. And many of these we have the subcategories of the different types of nanometals, nanometal oxides, etc. And the applications, which is extremely important from my perspective, is how are they being applied? What are they being used for? And a lot of these, as you can see, run a gamut as well, from basic engineering applications to systems applications to clinical applications in medical research. And that we found very interesting and of use as well. One of the things I wanted to talk about, just a quick show of hands. How many of you here are involved in an academic research environment of some form? Just a quick show of hands. Okay, it's about 50%. How many of you on the web? Raise your hands. I'm just kidding you. Trying to see how many rows they have. The academic research environment is a pretty unique environment. I think one of the things, it's not a constant process, and that's one of the things that makes it unique. Process change regularly. There's always process change going on because the nature of research is you don't get that million-dollar question answered with the first one. You try other avenues or you try different directions. So it's dynamic. It changes all the time. It changes the types of uses of materials in that environment. One of the other things is a regular turnover of personnel. Unlike an industrial laboratory, industrial research, much of the research at a university is based on the graduate students and the doctoral students and the postdoctoral fellows that are engaged in research at that university. At our institution, we estimate we have about a 3,000 person per year turnover in our research environment alone. About 3,000 between the graduate students, the doctoral students, and incoming students. That's about what it adds up to. That's a tremendous number of new personnel that we have to do, and that's over all types of research. Often these laboratories, well, almost every one of them, if you're a wet lab, already works with at least one of these, if not all of these types of agents. They work with biological agents, work with certain types of radiation-producing machines or radioisotopes, and new chemicals. So introducing a new item to them isn't necessarily foreign. I think in this case we're introducing something that's common but with new characteristics, and that is a little more foreign. One of the other things is there is already oversight in academic laboratories. There is regulatory oversight within that laboratory environment, regardless of the material that's being used. And this comes under the form of OSHA's laboratory standard. And the one unique thing about the OSHA laboratory standard is not a prescriptive approach to doing things. It's a performance approach saying, we'll allow you to describe how you're going to control your environment. We will then evaluate you on how well you do in controlling it against what you said you will control. And I think that's a very important element for a unique environment like a laboratory. And that's one of the things that federal OSHA ascribed to very early on. They recognize the difference between commercial entities and commercial production facilities and research laboratories. And that's something that's already there. The other thing that's a part of it is developing safety operating procedures, or SOPs, standard operating procedures, for the things that are done in a lab. Typically, this is already there. When you do an experiment, you have an experimental protocol. And one of the things we're trying to do is encourage and really try to integrate the safety protocols as a part of that experimental protocol, because rather than layer something else on top of the experimental protocol, it should be integrated within that protocol. And this is really an approach I think that's going to have the most long-term benefit when you have especially people that are learning in this academic laboratory go out and start working in industrial laboratories or doing pharmaceutical research or whatever, that they're going to have the ingrained thought process of looking at the different steps of their experimental protocol and looking at the safety processes that may accompany those steps. In industry, this is known as a process safety approach. And I think in research we haven't used it as much, and we need to start doing a lot more integration. So our approach is, how do you integrate this rather than creating a new layer of requirement, is try to integrate it within what you're already doing in the experimental process. And then the last is to utilize a risk-based approach for safety management as opposed to a one-size-fits-all prescriptive approach. Now, Paul showed an example of this earlier today, the typical risk assessment and risk management functions. I want to add one other element to this, and that's one of the things that's occurring. And another variable that can occur is risk perception. And one of the things that was identified early on in the development of nanotechnology is the potential for adverse risk perception to impact the ongoing scientific development and industrial and commercial development. And this is why it's very important for all of us to be communicating about this. Lux Research Corporation in 2005 estimated that up to 40% of the commercial and research development over the next 10 years, this is in 2005, between 2005 and 2015, could be, up to 40% could be affected by the perception of risk as opposed to actual risk. Even though actual risk is not yet known, the issue is whether perceptual risk could overwhelm whatever actual risk does occur. So there's something to be aware of there. And the third part is risk communication. And I think this is something also that we need to continue to focus on. Not only what the risks are, what we know about the risks and what we don't know. Both elements of that are part of risk communication. What that leads us to, as you've heard from Paul, and also we don't have a lot of quantitative risk information available yet. And so how do we make decisions? And we call that, doing qualitative risk management, which is not something you like to do, but it's something that oftentimes you are forced into doing. And there are things that we can do, however, to manage risk, at least manage it from a qualitative perspective. And as you gain more information and fill in the knowledge gaps, you can then alter that risk management program to accommodate those. So all this is decision making without all of the information necessary for quantitative risk assessment. And some of this does draw from experience practice. Some of it draws from analogous materials, etc. And experience and knowledge, expert experience and knowledge, really play a key role in a lot of this. As I said, working with hazardous materials in laboratories is not unique. There are all kinds of different types of hazards, including living nanomaterials. You have the viruses, etc., viral pathogens, etc., that can be worked with safely, just as anything else can. I'm not equating nanoparticles, the engineered nanoparticles to those yet, but I think it's something you just need to be aware of, that things can be managed safely. And a lot of that is developing the best practices or good practices for working safely with these materials. One approach, which we'll talk about briefly, is the use of a banding or a risk-based control process. That process pretty much follows this type of a line. I've tried to condense it here in looking at identifying the hazard. Once we go and identify the hazards, and with nanoparticles, you're really looking at a number of characteristics, some of which was discussed a little earlier, but you have the size, the morphology of the particle, the chemistry, the solubility, and toxicity. The dilemma we're running into with the particle, and this is especially true, as I said, I just came from a whole discussion on carbon. One of the issues that gets raised all the time, when is a carbon nanotube a carbon nanotube? Many times when you're doing applications, you functionalize that carbon nanotube, and does it then have the same characteristics as a non-functionalized carbon nanotube? Or is it now a new material? And that's a really critical issue, because one of the things you have to be careful of is encompassing everything under that one letterhead of carbon nanotube, when most applications use some functionalization. Not all of them, many of them use some functionalization of the carbon to gain its result. This is especially true in medical applications and clinical applications. So really understanding the particle and what we are actually working with that particle is extremely important. The second is the exposure potential. We just heard a really nice presentation on field evaluations. And I think the same thing is here. There are a number of things that you can look at in terms of developing some criteria for evaluating exposure potential. The actual total amount of material used is a good starting point. Is the potential there for it to become airborne? And we saw with many carbonaceous materials that are in open form, that's certainly a possibility. What's the number of persons at risk? I mean, when you're starting to look at it, is this something where the whole laboratory is involved? Although you still want to minimize it to as low as reasonably achievable. The duration of the experiment, the duration of the potential exposure period, and the frequency of operation. Is this something that's done daily, multi-times daily, weekly, monthly? Many experiments, one part of that process is done on a very sporadic, periodic basis. And so all of this goes into this area of evaluation to get to a risk level. And then you can look at assignment or procedure to a specific risk level. Now, typically before you do that, you also look at what are the control elements that can be applied to mitigate the risk. And these are the ranges. And then using this basis, this kind of a table as just an overall schematic, you can start applying some of these. One example of characterizing hazard, this is one, again, Lux Research did quite early on, but it still has a lot of applicability when you're doing a qualitative approach to this, is looking at the different characteristics that a particular type of particle. Along the top, you can look at the type of particle. Along the side, you have the characteristic of that particle, different evidences that might exist, and then do a qualitative basis of evidence. Is there evidence of this? Yes, somewhat, or no. And then what's the qualitative risk at the bottom across on a particle basis? This, again, was done a number of years ago. I think it still has some applicability when you're doing those types of things where you're not in a hard process, where you're working with one material for ongoing basis, 8, 10, 20 hours a day. So this is some way to at least put a risk characterization around the material. Other factors when you start looking at the exposure as well as the hazard include these, where you have across the top the occupational health hazard, which is somewhat what we just spoke about. What do we know about the particle itself? The quantity on the left side going from bottom to top, and then the physical state from on the bottom from left to right, and then the task duration. A lot of this goes into an overall risk assessment. And you know that the exposure risk typically increases as you go up and to the right. And this is just a way of characterizing, looking at a risk assessment process. And we had a good demonstration earlier about the hierarchy of controls, and I agree with that totally. I think also one of the things we overlook is the value, especially in short duration, short use types of environments, of administrative controls. Oftentimes somebody may try and do an experiment one time and that's it. It didn't do what they were needing it to do, and therefore they're going to get out of that work. That's not unusual. It does happen where they're moving on to something else. And so one of the things we're looking at is how do you really communicate within that. And so administrative controls to me include risk communication. And that's a key element, is hazard communication, risk communication, knowing what to do with the materials. I do make one note here, containers, how do you containerize through disposal? In California, lab waste actually by default is regulated as a hazardous waste unless you are able to declare it not a hazardous waste. And we can address that later if you'd like. Engineering controls, however, in a laboratory are a main set of control systems. And they have a range anywhere from working on the bench top without an engineering control, just general dilution, all the way up through fume hoods, glove bags, glove boxes, and ventilated weighing stations, as we saw. And then the other is personal protective equipment. Personal protective equipment is probably used in laboratories more simply because, again, the infrequent use, the lack of potential duration of a process, etc., is probably going to see more personal protective equipment used in laboratories than you will engineering controls, except for the high-risk items. So this is just an example of how something might look. This is not entirely filled in, where you can do the specific nanomaterial hazard ID. The type of exposure potential is based on what's going to happen, what's the nanomaterials that are going to happen with that particular material, and then what risk level. In this case, it might be in the low risk level because you're not doing anything abrasive. The solid nanoparticles are in composite or they're permanently bonded to a substrate, which is often what happens when you're first producing them. They are bonded to a substrate. These are not all the controls that would be in place, but just an example of some that would be used. Going up the ladder, you get to a medium, you have other conditions. May depend somewhat on the specific nanomaterial being used, but the other conditions of exposure potential here, whether you're working in liquid media during pouring or mixing or agitation. In that case, you might, depending upon all of the variables, you might work within a fume hood, within a glove bag, or within a glove box, depending upon all of the characteristics, along with other safety materials and practices within the laboratory. And then the last, if you're generating nanoparticles in gas phase, or you're manipulating particles in gas streams, or working with high potential for nanoparticle release into an exposed area, you go to the higher level. Many of these ranges, you'll see many control banding ranges using up to 5 bands. I think for laboratories that gets be a little excessive because you're trying to discriminate between very narrow ranges. And I think that, this is my personal opinion, that within laboratories you should be able to work within 3 bands. I believe NIOSH and some people at NIOSH have been looking at this as well and using laboratory bands 1 through 3. And they use this type of thing, which is a courtesy of NIOSH. You open from the open bench, the fume hood, to an enclosed system of some sort. One of the things we've done to try to help our principal investigators and our researchers is provide some practical safety guidance and advice. So we have 2 things. One is a research guide, practical safety guide, which contains elements from these right here, this list of items there. What are nanomaterials? Give a little background, and everything we put in there is also referenced literature. I think that's one of the things as a scientist who are working on science, they want to see what's your reference material, rather than just say, well, don't just tell us what to do, tell us what's the basis of this. And that's one of the things we try to do, and Mary Doherty at Stanford was very helpful and did a lot of detailed work with other universities to come up with this that we're using. And this is on our web there at the site listed at the bottom. It's available to anyone. So, and then we've developed out of that a standard operating procedure or template for working with nanomaterials. And this fits into the laboratory procedure. That's what I'm trying to get at earlier. We want it to fit within the experimental protocol. And what we look for is demographic information. Who's doing what? Where are they doing it? The process or equipment overview. What's being used, specifically the materials. How is it being used? We'll talk a little bit. There's a location for the specific experimental procedure. The risk assessment level, we ask the lab to assign this based on what they're doing. We don't review every one of these. What we look for are those that are going to be in a risk category 3 to be reviewed, but others we won't. And then the controls that they're going to assign. As much as anything else, this is a stepwise process for the lab. It's not for EH&S. It's for the lab to use, and that's really what we're trying to do. The step-by-step operating procedure, decon is very important. What do you do if there is a spill? Accident procedure, is there a decontamination process that's worked out and thought about ahead of time? And that's really the important part. And then waste disposal. Our default right now is all nanomaterials are regulated. we categorize them as regulated waste for now. And so that they are in the regulated waste stream and go out as in our hazardous waste stream. That's by our own definition. I don't think there's any regulatory definition as of yet, other than what I said earlier, that by default, laboratory waste is one of those categorical wastes in California. Training requirements, we do ask them what's the specific training requirements, and then are there required approvals. And this is on every lab protocol. We have certain items that require PI sign-off before the researchers, because you have many independent researchers within those labs that can do that research very well. I want to digress just for a brief moment here, very quickly, and talk a little bit about other areas where there is potential for impact in an academic research environment. Areas we don't often think about. Certainly laboratory animal research is a growing area. It's an area we need to have more nanomaterials used because that's where we're going to get our toxicity data. In our case, a lot of it is being used for medical application of nanomaterials. And so what we've started looking at is where are these other places on campuses, other than the research laboratory itself, where you may have implications for people that could be exposed. And this is one, you have the scientists themselves both, and in that case we're looking at the protocol submittals through, they're doing biological research that comes through, work with animals, come through the IACUC, the Institutional Animal Care Use Committee. And we also have representatives that sit on that committee, so we're able to identify when those come through. Animal husbandry personnel is another area. What do they do with the waste, and then laboratory animal occupational health program. I won't spend a lot of time. I just wanted to show this as an example. There are ancillary areas that we don't often think about that we need to be thinking about. Existing health and safety research of this area relative to the use of engineered nanomaterials is very limited, and so we're trying to focus a little more on that. One of the things we do focus on these types of areas for is for minimization of allergy and asthma related exposure. We know personnel that work with research animals have high propensity, a high proportion of potential for research for impact by allergy or asthma. And so we have to have a lot of activity going on to minimize that. One of the things we're contemplating, and I'll talk about this at the end here, about 5 minutes left, is the possible use of dander exposure, which is a exposure critical for evaluation of allergy or asthma. To use that as a surrogate for exposure, overall exposure of aerosols, including engineered nanomaterials. If we can demonstrate dander exposure is very low, we're going to know that any other aerosol exposure is probably low in those environments as well, because dander is very difficult to control. So I want to talk about one last thing, that's regulations. One of the things that's going on, we don't have a lot of significant or sufficient risk information. In this case, this is the emerging technology which has outpaced both risk characterization and government regulation at this point. And that's left organizations to develop their own principles, as was indicated earlier. Many people have developed their own OELs for application. Lastly, I just want to talk about a collaborative project going on with the Department of Toxic Substance Control, NIOSH, and California universities. And what we're attempting to do is, most universities have some form of guidance, but there's not a lot of consensus or sameness among them. So we're trying to develop, at least for California, in collaboration with DTSC and NIOSH, a set of practical safety guidelines for academic research that uses nanomaterials. These are the participants in this. You can see representation is a very broad scope across the academic research community of California, DTSC and Cal EPA, and NIOSH as well. And we'll talk about those relative roles, but in a very short, our objective in this is really operating in 3 phases. The first, identifying and reviewing existing pertinent nanosafety information and developing a set of draft guidelines. That's our first task, the phase, and the first team working on this is moving along with that. One of the first things they did was identify basically anything that existed relative to working with nanomaterials and the prospects of how you do that safely. That's an exhaustive list, and we're trying to wean through that. Phase 2 would be then evaluating and assessing the effectiveness of applying these guidelines in a variety of academic research settings. And this is where we're partnering with NIOSH in the hopes to be able to quantify how well these types of applications work, if we're recommending them, by doing it both at one level and then perhaps at another level, quantifying what the results of using controls at 2 levels and seeing which one actually is sufficient we'll work with that. And then 3, incorporating the results of the Phase 2 findings into finalization of the guidelines. So our deliverable at the bottom is to draft a practical set of guidelines for the safe use and disposition of nanomaterials in academic research environments in California. And we hope that this will have enough support and finding from this that it will catch on throughout other parts of the country as well. As many of you know, what starts in California often moves to other parts of the country. The last item on here, we will be publishing this. We don't have a date yet. We're working hard trying to move this forward and keep it moving forward. As you know, working with any volunteer group is always exciting and challenging at the same time because it takes, everyone has day jobs, and this we're working on as we can, but I think it's a very important project and for everyone involved. In addition to publishing these, we plan to post those also on the Good Nano Guide, and I just want to reference that as a very good resource. If you're not aware of it, this is a resource run out of ICON, the International Council on Nanotechnology, which is also out of Rice, but there's a lot of information put on here and on practical applications for using nanomaterials. With nanotechnology regulation, I just want to close with 2 slides here. One is, as you're developing regulation, we know regulation is going to be coming. The question is how fast and how hard, and that's a challenging thing to say. We really need to make sure it's coordinated. We also need to make sure the approaches are flexible and adaptive. That's one of the most challenging things with regulation, is creating it so it can be adaptive to changes in the science, especially when we don't know what the risk assessment is. The only place I've seen this successfully done, the only emerging technology, was recombinant DNA back in 1978. The scientists themselves convened and said, if we don't get ourselves around this, we know government will, and then we're going to be left with what they set in place at this point in time. And that showed us very much how what was perceived as a potential high-risk type of technology, actually the risk got, as risk information became more and more known, the risk level went way down. And it was because it was never put into a strict regulatory code that I believe that occurred. All right, last, life cycle approach is really critical. The balance and proportionality between costs and benefits of regulating is important, and then clarifying the accountability and ensuring transparency in the system is also good. The last slide is getting Nano Right in the lab is really important. Nano development is here to stay. It's not going to go away. The science is there, the development is there, the commercial applications are there, they're growing every day. And it's important for us to recognize that there are some engineered nanomaterials that will impact health in unique ways, just as the characteristics of the particles are creating unique opportunities in science and application. And it's how risk is assessed and managed that we need to really be challenged, and we are challenged right now. Working in laboratories with new, unique, potentially hazardous substances is not new, but new knowledge is needed to work as safely as possible. And then follow risk knowledge-based prudent practices and proven procedures. What I like to say is use credible risk assessment and responsible risk management. I think that's really the tune we need to build on. Credible risk assessment and responsible risk management. And the last is from a Howard Hughes researcher who made a very good statement on TV when he said, safe science is good science. So we want to practice both. So I want to thank you for that, and if there's time, we'll take a question. If not, we'll move on. Good deal. Back on time.
Did you have a question for that?
No. Okay. No, I'm sorry. We'll get back on time. Oh.
Thank you very much, Larry. I have a quick question. So with respect to the level of understanding in universities with respect to nano safety, what is your general impression? Because there has been a phase in nanotechnology where everything small was regarded as dangerous, which in the summary of for the NNI of what people perceive worldwide one important paradigm that has emerged is the concept small is dangerous is outdated, that it is very specific related to materials, material properties, their use, and that the current guidelines at least is constructed on that basis rather than a basis of just a perception that nano is dangerous.
I think that's still an educational need, even in the scientific community. We were talking about that yesterday. I used the example. Benzene we know is hazardous, but if you add a group to a benzene, it becomes an entirely new material. It may become toluene, depending what you add to it, and that has different properties from benzene. And I think what we're going to see in this, some of the similar things happening, even though, and that's less size than it is characteristic. But I think all of those are going to play a role that we're going to have to really work on, because we know sometimes the base material may have certain conditions and properties, but if you do a simple manipulation of that, you can change those properties very easily. I don't know that it's universal that size is the main indicator of hazard, but I do think we have scientists coming from different disciplines. Certainly those that have grown up with organic synthesis chemistry know about the changes that take place. Those that are now working in nanotechnology come from all over the field. You saw the different departments working. And this is the same concern we have when we have people from environmental engineering or different engineering start wanting to work with pathogens. And it's the same type of transfer where they're used to working in one environment, now they're moving into an environment that has other variables that they're not as familiar with but need to become more familiar with. I think that's the same thing that has to happen here. It's not just a size change, it's a whole set of characteristic changes that have occurred that people have to become more versed with. When nanotechnology was first taking place about 10 years ago, I was most worried about the non-chemists and non-material scientists coming over to work, because not of the products they're creating, but of the tools they're using. Because a lot of times if you were developing nanomaterials, you were using very toxic gases, you were using other materials that have hazards associated with them, and they hadn't familiarize themselves necessarily with the tools to do that work. Then the last is an area of nanotechnology we've not even talked about today, which I have more of a concern about if it's not managed properly, is synthetic biology. That's another nano development that's going on, where you're actually creating living organisms from non-living materials. And I think that's an area that we're going to see more and more rapid growth in as well. And much of that is done also at the nano level.
We have a question from the web, one of our web viewers. How did you come up with the risk levels? Did you assign different characteristics with some weighing factors?
That's one of the things that the group is working on right now. We will be working on some of that. I'm not sure it will have a weighting factor per se, and I think some of this will be still be somewhat qualitative. But I think there are ways, and there is certainly a full quantitative way out there right now that researchers at Lawrence Livermore, Sam Pack, and others have developed that use a very quantitative way, at least semi-quantitative way, of assigning risk factors to the control banding. That's not been defined yet. We don't define it in terms of a quantitative level, though, especially when you only have 3 bands. When you start getting into defining with quantitation, you're going to end up with many more bands than that. So no, we don't use quantitation at this point. Yes.
Can you speak to the microphone so people online can hear you?
Larry, following on from the previous discussion, since we're not going to be able to conduct toxicologic studies of every different type of nanoparticle, we're probably going to need some sort of categorical approaches in setting limits or some other approach. What's your feeling about that?
I mean, that's the dilemma. Well, my first feeling is there's not enough money going into risk assessment, and it really needs to step up. I mean, the country has to step up. I think our government has to step up, because we're not going to get good information and good data unless we do good risk assessment. I think categorical, I have a real problem with the categorical assignment of carbon nanotubes to all carbon nanotubes, because, as I said there, the properties are going to change as soon as you change that nanotube structure. By putting either functionalizing it in some way. That changes, and we're seeing that already in the medical studies, where carbon nanotubes are being used as a carrier for delivery of pharmaceuticals to specific sites. They're functionalized to go to that specific site, and we're seeing they're being cleared from the body. And so that's some of the challenges we're going to be faced with, because a carbon nanotube unless it's a raw carbon nanotube, is going to have different properties. And intentionally, that's why it's engineered. The thing we need to be able to do is to say, if the raw carbon nanotube is our problem, can we create and engineer it in a way that has properties that don't carry that same level of risk? And that's the thing that if we focus our efforts, especially the research effort, on identifying what is it that creates that risk, maybe there may then be ways to engineer that out as part of the engineering process of manufacturing.
Yes. Do you have any idea in the academic curriculum what kind of depth of treatment nanoparticles and kind of materials have in terms of industrial hygiene, engineering, toxicology, and material science?
I think it's very light right now. I think there are some where there's a little more information, but I would say it's quite light from my knowledge of it. I think one of the things, it depends which discipline it's occurring in, if it's in material science or maybe a little more, but I don't think, my belief is there's not a lot going on right now, and except for the part where they're talking about process safety. And typically, chem engineers and others don't talk about that until they're getting to large-scale industrial application. So this is where we're trying to promote it at the research level. As a part of the experimental process, you want to incorporate safety elements as a part of that process, which means looking at each step, including the material that you're working with and the material you're developing. So I don't think it's very heavy at this point.
We have a question in the back.
Hi. I perceive this more as a question of a problem with the actual disposal of these materials or substances than even cleanup at the site, which is important. And we're just, it seems, beginning to address the anomalies in that. What happens, though, once they're collected? I mean, the speaker prior to you even admitted that prior to now, up to now, there are no regulations whatsoever, and that bears fruit with what you said, where, you know, technology has far surpassed government and their ability to regulate because of their lack of knowledge and not being directly involved with it. And so that when it is collected, what do you do with it then? And how do you assure that perhaps some of these substances or particles don't commingle and mix and create a massive soup of something that would be like one of the Superfund cleanup toxic waste dumps that we had to deal with in the last several decades?
I don't mean to make that, you mean a nano Superfund. Okay. No. Couple of things. One is, I think that, and I can't speak for what everyone is doing. As I said, in our case, we've decided to treat anything related as regulated hazardous waste, and that then goes out for industrial incineration. Incineration will oxidize the material and does take care of it. I'm not saying that's the only way it could be disposed of. I think the second part is, when you're talking about amounts used, the amounts used are so slight. I mean, it's very, in academic research, you're talking about milligrams over the course of months. And so the amounts, when you start looking at them, are very, very small. That's now. Not in the industrial use. Absolutely. And there's actually a lot of research going on in this area of what is going to be the environmental fate. And I think that's a very important point to make. What what NIOSH is looking at and others, EPA is looking at, and DTSC is also concerned about what's the environmental fate. And that's an extremely important element as well. I don't disagree with you at all on that.